everyone, welcome to the channel. In today's video we're going to be looking at how to solve a differential equation with a Dirac delta in it using Laplace transforms. So let's get to it. Here's our differential equation. You see we've got a second order differential equation equal to this Dirac delta here. So the way we solve the differential equation using Laplace transforms is the same way as we've always done. You have a differential equation which is in terms of time. This is your independent variable, which means that you're sitting in the time domain. When you apply your Laplace transform, you are taking it into the S domain or frequency domain. Once you're in the frequency domain, you want to simplify so that you can then find the inverse Laplace transform in order to get back into the time domain. So the first step is to take the Laplace transform of both sides of the equation. So the Laplace transform of your second order derivative is going to be s y of s squared minus sy at 0 minus y dash at 0. Then the Laplace transform of the first derivative is going to be sy of s minus y at 0 plus 5 times the transform. And that is going to be equal to, here you have the Dirac delta, so that is going to be e to the minus s. Okay, so now we can simplify our left-hand side because you see you have initial conditions. So y at 0 is going to be 0. Y, the derivative at 0 is going to be 0 also. So we end up with s squared y of s plus 4 s y of s plus 5 y of s equals e to the minus s. And then we want to isolate the y of s, which is the transform on your left-hand side. So we'll have y of s squared plus 4s plus 5, because we factorize, and that is going to equal minus s, which means our transform is equal to e to the minus s over s squared plus 4s plus 5. So now what we want to do, because this is now in our frequency domain, you see your variable is s, it means you're in your frequency domain. We want to go back into our time domain. So we now need to find the inverse Laplace transform. And when we do this, if you look at the function, because we have e to the power minus s over this trinomial, we know that we're working with a discontinuous function. Well, we'd know that from the initial differential equation anyway. But what it means is when we find the inverse, we have to separate the exponent from the rest of the expression. Because then we find the inverse Laplace transform of this, just ignoring the exponent. Now, if you look at this fraction, we always start with our denominator. So the denominator here is a trinomial. You can't factorize this, which means you need to use completion of the square. So that is going to be equal to s plus 2 squared plus 1. Right? So then your function y of t, after you take the inverse Laplace transform, is going to be, you know that the shift here, e to the minus s tells you what the shift is. So you know that's going to be u of t minus 1. Then the function in front of it is going to be the inverse of this fraction, the inverse Laplace transform of this fraction. And the inverse of this is where you have an exponent times the sine function. The power in this case is going to be minus 2t, but if we include the shift, it's going to be t minus 1 times sine of a is 1 in this case, if you're looking at your formula sheet. So it's going to be 1 times t, but in this case, you have to include your shift. And that is the solution to your differential equation. So you see that the first part of the solution to this is where you would look at your Dirac delta. Right, so finding the transform of this would be new. But once you've done that, when you find your inverse Laplace transform, it's really the same method you would use for your Heaviside step function. I hope that was helpful. I will see you in the next video. See you then. Bye.